When you think about PKI, everything ultimately depends on how well you protect the private keys. A hardware security module, or HSM, is a specialized physical device built exactly for that job. It generates keys inside a secure chip, uses them for cryptographic operations, and never lets those private keys leave the hardware in plain form. Strong authentication controls who can use the device, and tamper-resistant casing helps ensure that if someone tries to open or modify it, the keys are wiped or made unusable. These devices are tested and certified against standards like FIPS 140, so organizations can anchor their root of trust in hardened, auditable hardware. The trade-off is cost and complexity, but for high-value systems, HSMs are often non-negotiable. Behind any HSM decision is a simple question. Where do your most sensitive keys live? And who are you willing to trust with them? An on-premises HSM is like a vault you own and operate yourself. You get maximum control and very strong security guarantees. But you also carry the highest cost and need specialists to deploy, patch, and monitor it. This model fits highly regulated environments, or places where keys simply must not leave the data center. Cloud HSMs shift that model. The cloud provider hosts the hardware, gives you strong isolation, and lets you scale up or down as needed. You move from heavy upfront spend to a pay-as-you-go model. The trade-off is reliance on the vendor's platform, processes, and availability, and less fine-grained control over the hardware itself. Software or virtual HSMs lean towards flexibility and speed. They're inexpensive, easy to automate, and great for dev, test, or very high-scale workloads. But keys often end up in system memory, so your security assurance is lower, and you're more exposed if the host is compromised. As we go deeper into PKI, keep this spectrum in mind. High security and control with on-prem HSMs, balanced cloud options in the middle, and highly flexible but less trusted software approaches. Every PKI design is choosing a point on that spectrum, based on risk, cost of, and operational maturity. FIPS 140 is really about how much you can trust a cryptographic device, like an HSM, to protect your keys. It's a US government standard that defines security requirements and uses independent labs to verify that vendors actually meet them. The current version is FIPS 403, which replaces 103.2 and tightens many of the rules. The key idea is the security levels. Level 1 is basically software-based protection with minimal physical security. Level 2 adds tamper evidence, so you can see if someone has tried to open or modify the device. Level 3, which is what most certificate authorities and serious PKI deployments target, adds active tamper detection and response. If the device is opened or probed, it zeroises the keys so they can't be stolen. Level 4 goes even further and protects against harsh environmental attacks, like extreme temperature or voltage changes. Moving up the levels brings stronger assurance, but also higher hardware cost and more operational complexity. In banking, payments, and government, those higher levels are often mandatory. For PKI architects, the important point is that your choice of FIPS level directly affects both your risk posture and your cost model. Running your own on-premises HSM means you take direct responsibility for both the physical and logical security of your most sensitive keys. Think of the HSM as a dedicated appliance in a secure cage or safe room, cabled into your data center network. It exposes a management interface for security officers and admins, and a separate secured network path that your applications use to request cryptographic operations. Operationally, 3 things really matter. First, hardware setup, correct rack mounting, redundant power, and tamper-evident physical protections. Second, procedures, clearly separated roles for security officers who control key material, and system administrators who manage the device, so no single person can do everything. Third, troubleshooting basics, verify network connectivity end-to-end, then rely on the HSM's logs and alerts to diagnose issues, rather than poking around inside the device. With these foundations in place, on-prem HSMs can give you very strong control and assurance over your private keys, in exchange for more operational responsibility compared to cloud HSM services. Moving HSMs into the cloud is a trade-off between control, integration, and cost. AWS Cloud HSM gives you dedicated hardware with very strong security and tight integration into the AWS ecosystem. It suits teams that want cloud convenience but still need strong isolation and control of keys, for example, for financial or government workloads. Azure's dedicated HSM offers a similar security profile with a strong pull for Microsoft-centric enterprises. Its main attraction is alignment with Azure compliance frameworks and audit expectations, especially when regulatory requirements are very strict and you already operate heavily in Azure. Google Cloud's HSM is more fully managed. You give up some hardware-level control, but you gain simplicity, automation, and usually a more flexible cost profile. This works well for cloud-native teams that prioritize ease of use and high-velocity deployment. Across all three, the big architectural shift is from buying and running your own hardware, with heavy upfront capital expense, to renting cryptographic capacity as an operating expense. For PKI and key management, that makes it easier to scale, to automate key operations, and to align HSM usage with your broader cloud strategy, provided you consciously choose the right mix of control, compliance, and cost. Hardware security modules are where the theory of key protection becomes real. You can think of them as highly guarded vaults for cryptographic keys, but with built-in computing power. Anytime a private key is so sensitive that its compromise would be catastrophic, you want it inside an HSM. That includes the private keys of your certificate authorities in a PKI, keys that protect TLS and HTTPS at scale, and keys that encrypt entire databases. The HSM generates these keys with strong randomness, keeps them non-exportable, and performs operations like signing and decryption inside the device, so the key material never appears in server memory. You'll also see HSMs behind high-value business processes, signing financial transactions, issuing identities for IoT devices, securing code signing keys used for software updates, and protecting secrets for API authentication. Across all of these, the pattern is the same. Move the crown jewel keys into a hardened, auditable environment, and let applications call the HSM instead of touching the keys directly. Once HSMs are part of your PKI design, performance and scalability become just as important as security. Two numbers matter most: throughput and latency. Throughput is how many cryptographic operations you can do per second. Latency is how long each operation takes, end to end. A single HSM can deliver very high throughput, but only up to a point. As transaction volume grows, you eventually hit a bottleneck, where the crypto queue backs up and your application slows down. To push past that, you scale out rather than up. The first strategy is load balancing. Instead of sending all signing or decryption requests to one box, you distribute them across a cluster of HSMs, so overall capacity grows as you add units. The second strategy is partitioning. You carve one physical HSM into multiple logical slots, so different applications or tenants get isolated environments, while still sharing the same hardware. Architecturally, the trick is knowing when the HSM is becoming the bottleneck, then offloading non-critical operations and keeping only true key protecting tasks inside the HSM. That's how you maintain strong security, without sacrificing responsiveness at scale. When you secure private keys, it's easy to focus on the HSM box, but real protection is layered like an onion. At the very center is the key material itself. Everything else exists to protect that data, and to make sure that if something goes wrong, those keys are wiped or made unusable. That's where tamper response and sensors come in. They detect abnormal voltage, opening the case, or other physical attacks, and immediately zeroize the keys. Around that, you need strong access control, so only authorized people and systems can trigger operations with the keys. That usually means smart cards or dedicated tokens for admins, and strict role-based access, so no single person can do everything. Next is the surrounding network. You isolate these systems, limit interfaces, and place them behind firewalls and private subnets, so they're not casually reachable. On top of the technical controls, you add physical security, locked rooms, surveillance, and simple but effective procedures, like visitor logs. Finally, there's the process layer. How backups are handled, how escrow works, and how you enforce split knowledge and dual control, so that critical actions always require more than one trusted person. All of these layers together are what actually protect PKI keys in the real world. The hardware alone is never enough. Choosing an HSM is less about brand names and more about matching risk, budget, and operations. Start by being very clear on your requirements. Do you actually need strong certifications like FIPS 400T to or 100FT3 Level 3? Or is that only required for a subset of keys, such as root says or payment keys? If the answer is yes, you're usually looking at a dedicated, often on-prem or specialized cloud HSM, and you should expect higher cost and more operational overhead in exchange for assurance. If you don't need that level of certification, cost and flexibility become the main drivers. In that case, software-based key management or general cloud HSM services can be perfectly acceptable, especially for application-level or short-lived keys. Across vendors, evaluate three things carefully: security properties and certifications, integration and API support for your tech stack, and total lifecycle cost, including operations and vendor lock-in. The right HSM is the one that meets your compliance bar, while still being easy enough for your teams to use consistently, so keys don't drift into weaker shadow storage over time. Once you move from designing an HSM deployment to actually running it, the focus shifts to disciplined, repeatable operations. Day to day, you're watching health and logs. You check that HSMs are online, performing within expected limits, and that access patterns in the logs match what you'd expect from your PKI applications. Strange spikes, failed logins, or unexpected key usage are early indicators of abuse or misconfiguration. Next is backup and recovery. Key materials stored in HSMs must have secure, encrypted backups, often to separate devices or secure vaults. You want to be able to lose an HSM and still recover your keys, without ever exposing them in plain text or bypassing dual control processes. Regular recovery drills are essential, so you know the process works under pressure. Firmware updates are your most sensitive change. New firmware can fix vulnerabilities or add algorithms, but it can also brick a device or violate compliance if not validated. Treat firmware upgrades like any critical change. Test in a non-production environment. Plan maintenance windows, and have a clear rollback strategy. Finally, audits and compliance keep you honest. Periodically, you review access logs, role assignments, and configuration against standards like FIPS or PCI, and against your own policies. A common pattern is leikofikadat sheaves, audispravits, and family stone. Health is checked at least monthly, and full compliance audits happen on a longer, typically annual cycle. Together, these practices turn HSMs from a secure box in the rack into a well-governed trust anchor for your PKI. To see how HSMs fit into your systems, it helps to think in three layers. At the top, your applications just want to sign or decrypt data. They don't care how cryptography happens. They send, "Here is some data, please sign it with key X," and expect a result. In the middle sits a translation layer, middleware and standard crypto APIs. Interfaces like PKCS number 11, Java's JCE, or Windows CNG take those high-level requests and convert them into low-level commands the HSM understands. This bridge lets you swap one HSM for another with minimal code changes, as long as you stay within the standard interfaces. At the bottom, the HSM hardware performs the actual cryptographic operations and never lets private keys leave the secure boundary. Only results come back out: signatures, decrypted data, or public keys. In cloud environments, providers often hide most of this middleware behind simple SDKs or REST APIs. But the pattern is the same everywhere. Applications call a standard API. Middleware turns that into HSM commands, and the HSM protects the keys while doing the heavy cryptographic lifting. When you operationalize PKI, most failures don't come from cryptography. They come from how you run the system day to day. Initialization is a good example. Setting up routes, HSMs, and admin roles is complex, so mature teams use formal scripted key ceremonies. Every step is documented, witnessed, and repeatable, which sharply reduces the chance of hidden mistakes. Key loss or disaster is another existential risk. Instead of a single backup, you use M of N schemes and split knowledge, so no one person can reconstruct a key, but the organization can still recover if something goes badly wrong. At scale, PKI can also become a performance bottleneck. The fix is to design for capacity from the start, load balance signing and OCSP, and partition workloads, so that spikes in one area don't take the whole trust system down. Integration often stalls projects, so you lean on standards and proven libraries. Interfaces like PKCS number 11 and well-tested SDKs mean applications don't each invent their own insecure way to talk to keys. Compliance shouldn't be an annual fire drill. Continuous logging, monitoring, and internal reviews mean that when auditors arrive, you're simply exporting evidence from controls you already rely on to run the PKI safely. Let's pull together the big ideas about HSMs. First, the value. HSMs earn their place because they keep private keys physically separated from your applications and admins. That isolation makes them the root of trust for your PKI and other critical crypto operations. If the HSM is trustworthy, everything built on top of it can be trustworthy. Second, how to choose. Think in terms of risk, not fashion. On-prem HSMs give you maximum control and customization, but you also own all the complexity. Cloud HSMs trade some of that control for scalability, easier management, and faster time to value. The right answer depends on your regulatory constraints, threat model, and team maturity. Finally, implementation is where most failures happen. The hardware alone will not save you. You need strong procedures, dual control over sensitive actions, robust change management, and regular audits. HSMs provide the tools for high assurance, but disciplined operations are what actually deliver it. You've now seen what HSMs can do for you technically. Now let's translate that into your own environment. Start by identifying which keys, if compromised, would stop your business, damage your brand, or trigger a regulatory incident. Those are your crown jewels: root and issuing CA keys, code signing keys, high-value TLS or VPN keys, and keys used for payments or tokens. Next, be honest about where those keys actually live today. Are they truly generated and stored inside certified hardware, or are they sitting in software key stores, VMs, or config files that could be copied, snapshotted, or exfiltrated? If an attacker got admin access to a host, could they walk away with a usable key? Finally, consider resilience. If an HSM or other physical device fails, what happens? Do you have secure backups, documented recovery steps, and people who know how to execute them without breaking your trust model or violating compliance rules? Keep those 3 points in mind, because in the next module, we'll build on them and look at how key custody, governance, and separation of duties turn HSM technology into a complete control system.